Okay, so let's do a quick recap before we proceed. So in the last couple of classes, we investigated this new notion of learnability called non-uniform learnability. We are in the setting where agnostic pack learning is not possible. Again, we're primarily looking at binary classification with 0-1 loss. All right, so we know that hypothesis class is agnostic pack learnable if and only if the VC dimension is finite. So suppose that we are provided a hypothesis class for which the VC dimension is infinite, then what can we do? And for certain hypothesis classes, even if the VC dimension is infinite, we can't of course get agnostic pack learnability, but maybe we get something a little better than nothing. Right? And so for this we defined non-uniform learnability, wherein in some sense the rate of convergence of the generalization error of, let's say, a good predictor is maybe not epsilon close to every single hypothesis within the class, but it's at least better than something which depends on the number of samples. So if you have a certain number of samples, then you're guaranteed that you're going to do at least as well as epsilon close to the best predictor within some subclass of the hypothesis class. And as the number of samples keep increasing, the size of the subclass also keeps increasing. You're going to do better and better than many more predictors within your hypothesis class. Right? And we saw that non-uniform learnability is only possible if you can express the hypothesis class as a countable union of agnostic pack learnable hypothesis classes. And for such hypothesis classes, we also have a learner. ERM is not going to work because ERM would look through the entire hypothesis class and look for the one that minimizes the empirical risk. But as we know, if the VC dimension is infinite, there's the genuine problem of overfitting if I just use ERM. And certainly it's not going to give a good non-uniform learner. But with a little bit of a tweak, essentially with a regularization term, we can get non-uniform learnability, even if the VC dimension is infinite. If the VC dimension is finite, then you don't have to do anything else. You just use ERM and you're done. But now if the VC dimension is infinite, then you can use structural risk minimization, wherein you minimize a linear combination of the empirical risk and another term, which in some sense measures the complexity of the subclass within the hypothesis class. Right? So for every h, let's try to recall the definition of epsilon k of h. So for the kth subclass, right? After all, we are assuming that the hypothesis class can be written as a union of countably infinitely many agnostic pack learnable classes, and the kth class is h sub k, and we defined epsilon k of n comma delta as the smallest epsilon, such that the sample complexity for uniform convergence is less than or equal to n. Right? And this basically corresponds to the regularization term. The other thing to keep in mind is this k of h is the first k such that this little h belongs to h sub k. Right? That's one way of thinking about it. Correct.
But there is only one function h.
Correct, but you're minimizing for every h, there is an epsilon k of h. Alright? So for every predictor within your hypothesis class, there could be uncountably many predictors in your hypothesis class. For every such h, there is some number. This corresponds to some number. For a given n and delta and weight function, this quantity is well defined. Alright. So this is for every function there is one such thing. Alright. For every h in your hypothesis class, you have this quantity, which really depends on K, right? Which subclass it belongs to. So effectively, this quantity is purely dependent on the subclass. This K of H is used to denote that this is the first, so a given predictor could potentially belong to many subclasses, which is okay, right?
So K is the index for subclass.
The K is the index for the subclass, and K of H denotes the index of the subclass to which H belongs to, or one such subclass that H belongs to. Okay, but any other questions? So in defining structural risk minimization, we also required this quantity, the weight function, right? So recall that the weight function is any sequence of non-negative numbers which sums to something which is less than or equal to 1. And as long as you have any such weight function, you can give guarantees on the generalization error of structural risk minimization. So then how do you choose the weight function? Is there some natural way of choosing the weight function? Or, because every choice of weight function will give you a slightly different bound for the generalization error, right? So for this, let's look at a slightly simpler example where the hypothesis class itself consists of just countably infinitely many predictors. So there are whatever H1, H2 and so on. There are countably infinitely many such predictors in my hypothesis class. Of course, I'm implicitly assuming that the hypothesis class has infinite VC dimension, right? Otherwise, there's nothing more to do. Now, I can view this also as a countable union of pack learnable classes, because I can take each HI to be one subclass. There's nothing stopping me from this. It's a trivial subclass, but still it's a pack learnable class. 1 to infinity HI. Right? Now, if I were to try to use the generalization bound that I have over here, what is the corresponding epsilon that I would choose? Right? Or let me put it another way. So what would be epsilon k of n delta? How can you choose or get a bound on epsilon k of n comma delta?
Something with hs of x minus hi of x.
So purely, let me put it in another way. That's the quantity that we have. That it's r of hs minus rs of h, but that's not what we're interested in, right? We want a concrete bound that depends on n and delta. All right. What is the definition of epsilon k of n comma delta? It is. Where did I have it? Yeah. So basically, if I have n samples, right? If I have n samples and I want uniform convergence within the subclass, that is rs of h minus r of h should be within epsilon for every h, and this should happen with probability at least 1 minus delta, right? So then how would you get a bound on that epsilon for this specific example? What would you use? But how do you get the risks? That's a random quantity, right? Basically, it amounts to bounding what is the probability that R of hi, because each subclass only consists of a single predictor, Rs of hi less than or equal to epsilon should be at least 1 minus delta, or maybe if I take the negative, greater than or equal to epsilon should be less than or equal to delta. Right? And I want the epsilon in terms of n and delta. For a given delta and n, what is the smallest epsilon that I can achieve? So how do you get a bound on this particular quantity? Yeah, Hoeffding's inequality. Right? And we know that by Hoeffding's inequality, this is less than or equal to 2 times. Again, there's a single predictor, so there's nothing complicated going on over here. Right? So it's just 2 e to the power minus some constant epsilon square times n. Right? You can just use the whatever Chernoff bound for Bernoulli random variables if you want, because we're only looking at 0-1 loss. Right? And they're all IID. So what is the corresponding epsilon in terms of delta and n? So it's square root of, okay, if you want to do it step by step, I have 2 over delta less than or equal to e to the power minus plus c epsilon square n. So epsilon is basically square root of log 2 over delta divided by n times there's a constant involved, so c prime. Where c prime is a universal constant. So as long as epsilon is greater than or equal to this, you are guaranteed that the probability is at least 1 minus delta. Right? So in other words, my epsilon k of n comma delta is precisely this quantity. It is some universal constant times square root of log 2 over delta divided by n. And if I had to get a bound on the generalization error of the SRM, the structural risk minimization predictor, then that quantity would be epsilon k of hs time of n comma w k of hs times delta. So for the SRM, R of hs is going to be less than or equal to Rs or R of h, this Rs of h plus constant square root log 2 over w k of hs times delta divided by n. also R of HS is less than or equal to R of H plus universal constant times log 2 over Wk of H times delta divided by n for all H such that this is greater than or equal to 1 minus delta. Right. I can write this as R of Hs is less than or equal to R of H plus constant square root minus log Wk of H plus log 2 over delta divided by n. So in the end, the bound on the generalization error depends on this quantity, on this weight function, how you choose the weight function, right? So how do we go? Is there a natural way of choosing the weight function? There's no unique way, and it's difficult to say that there's one right way to choose the weight function. But there is one natural principle that is generally used, or a natural principle for choosing the weight function, which has its roots in data compression. All right. So we'll take a little bit of a detour, to study what are called prefix-free codes. So let's suppose that we are given an arbitrary set we're given some arbitrary set A and some map from the set A to the set of all binary strings of arbitrary lengths. All right. So F takes some symbol from A as input and outputs a binary string of some length. The length of this string may not be the same for all symbols. It could be different. Right. So we say that F is prefix free, or F has the prefix free property if F of x1 is not a prefix of any other f of x, so you pick any two symbols which are distinct. Then the function value or the string that corresponds to one of the symbols cannot be a prefix or for the string for any other symbol. Okay, hopefully the definition is clear. So for any prefix-free code, it turns out that this is a special property. Now, there's no unique way of generating a prefix-free code. Right? There can be multiple such functions. But as it turns out, the lengths corresponding to a prefix-free code satisfies a special property. Right? So if f is prefix-free, and let's say that this mod f of x denotes the length of f of x. Then when you sum 2 to the power minus the length of f of x over all possible x, this quantity is guaranteed to be less than or equal to 1. Yeah? But you're summing over all. So for example, you mean to say just the fact that f of x has length greater than 1 is enough to guarantee this? Okay, so let's consider the set of all possible strings of length at most, say 3 or even 2. So let's consider 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay? Is it if I'm not even taking all possible infinite strings, right? Just these 6 strings. Let's try to compute 2 to the minus the length of f of x. What would that be? Yeah, so you have half plus 1/4 plus 1/4 plus so on, you get 2. Right? So the prefix property is necessary. If it doesn't satisfy the prefix property, then you don't have this guarantee anymore. Correct, exactly. So it's not prefix free. But then you can come up with any prefix free code. For example, 0, 1, 0, 1, 1, 0, 1, 1, 1. Right? This is prefix free.
So I think the definition you should have a minus in the definition 16 and 5.
Why do you mean? What do you mean a minus?
Belonging to a minus set of x because it can match to itself.
Yeah, it's not equal.
So x1 is not equal to x. Yeah, so basically you take any two distinct symbols, then the corresponding mapping, one is not a prefix of the other. So if you sum these, if you sum the lengths or the sum the inverse 2 to the power lengths, then you get half plus 1/4 plus 1/8 plus 1/8, which is exactly equal to 1. Right? And because this is prefix free, so this satisfies Kraft's inequality. how do we prove Kraft's inequality? So it's a very intuitive proof. So let's take a binary tree, okay, of which extends infinitely. Okay. Now we are assuming now each of these f of x it has finite length, right? So you can label the vertices of this particular tree by f of x. Right. So suppose let's take this very specific example. Right. So have 0, so 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. It potentially extends all the way up to infinity. But so 0 is one such, let me call this x1. Right, so I have 1, 0, which is the other symbol. I'll call this x2. And then 1, 1, 0 is x3. And 1, 1, 1 is x4. Okay, so using this method, I take this tree of infinite depth, and then I label some of the vertices using symbols. All right. So now, so this particular labeling has the property that no symbol is going to be a descendant of any other symbol. That is satisfied by the prefix property, because no string is a prefix of any other string. Therefore, no symbol can be a descendant. It can't go below any other symbol.
Special cases when all of them are in the same row,
Huh.
then they'll be equal to 1. If they all are in the same row, same things, then the inequality becomes 1.
You can say something even more. Basically, if every vertex has an answer, so if you take the infinite depth tree, if every leaf, I'm speaking very, very loosely over here, has an ancestor which is a symbol, then it will sum to 1. They don't even have to be at the same level. Right? In this case, they are not at the same level. Right? Anyway, that aside, so now, well, this is how I constructed this particular tree. Now, let me consider a random process, which is basically just an IID Bernoulli string. So I keep flipping coins, a fair coin. So I generate a sequence of zeros and ones, and I keep flipping until I hit one of the symbols. Okay. So let's generate a process. Let me call it y1, y2, y3, and so on, where each yi is IID Bernoulli half. So let's call this y star until y star is f of x for some x. Basically, you start with the root, and then you generate the first bit, and then you see, is this one of the labeled nodes? If yes, then you stop. If it is not one of the labeled nodes, then you keep proceeding. You go to the, you started out over here, you started with the root, and then you flipped, and you maybe if you got a 0, then you stop. If you got a 1, then you move, you traverse down the tree, and then again flip the next bit. If you got a 0, then you stopped. If not, you traverse down the tree, and so on. You keep traversing down the tree until you hit, so it's a random walk down the tree until you hit a labeled node. Okay. So what is the probability of that y star is equal to f of x for any particular x? Correct. So 1 by 2 whole to the power length of f of x. So it is just 2 to the minus length of f of x, right? Which is exactly the quantity that I have over here. Now, I have the special property that no matter what happens, with positive probability, I will hit one of the xi's. Right? That has to happen. This is not guaranteed if one of the nodes is a descendant of the other, because then there's a possibility that it will never reach that symbol, because once it reaches the ancestor, it's never going to go down. All right? So this is exactly equal to this, and the events that y star is equal to f of x and y star is equal to some f of x prime, they are mutually exclusive. All right? The intersection is empty. So now one thing to note is that it's possible that you never hit any of the symbols. With positive probability, you are going to hit. So for every symbol, the probability of reaching that symbol is positive. It's exactly equal to 2 to the power minus length of f of x. But then it is definitely possible that maybe there is no symbol down that particular path. For example, if I replace this example with just 1 0, 1 1 0, 1 1 1, if the first bit is a 0, then you'll keep proceeding forever without hitting a symbol, which is okay. But no matter what happens, the sum of these probabilities, this is definitely going to be less than or equal to 1. Because these events are all mutually exclusive, the probability of the union, which is the probability that you hit at least one of these symbols, is equal to the sum of the probabilities. But the probability of the union, it doesn't cover everything. Need not cover everything, depending on how you did the labeling in the first place. But no matter what happens, the total probability has to be less than or equal to 1. And that's it. That's Kraft's inequality. Now, as it turns out, there is a slight generalization of Kraft's inequality to not just prefix-free codes, but also what are called uniquely decodable codes. So prefix-free codes are those for which the code word or the binary sequence corresponding to one symbol cannot be a prefix of the binary sequence corresponding to any other symbol. But you can generalize this. Essentially, if you take variable length binary strings such that once you reach the end of the sequence, you can exactly uniquely determine which symbol that belongs to. So potentially, maybe you have to look a couple of symbols in the future to decide whether this is the one corresponding to that symbol or not. All right. Let's not worry about the exact definition, but as it turns out that even uniquely decodable codes satisfy Kraft's inequality.
other examples, like apart from suffix?
I can't think immediately of a non-trivial example of a uniquely decodable code that is not prefix free. Yeah, I'll maybe share it later. But I mean, the point is that there are so-called uniquely decodable codes that are not prefix free. Okay, so this means that I can define, I have this Crafts inequality, right? And now what I want to do is use 2 to the power minus length of f of x as a weight function. Okay? So we'll choose. So what's the goal of defining all of this? So given the hypothesis class H, which is H1, H2, and so on, some countably infinite hypothesis class, I'll have a prefix-free code for this particular class. And then we'll choose wk to be 2 to the power minus length of f of xk. If it is prefix free, then it satisfies Crafts inequality, and this is a valid weight function. Okay. So why go through all of this procedure, right? Now, a prefix-free code, so it's a natural way of, you can think of f as describing the particular predictor h. Okay, let's look at a more natural example. All right. So suppose that suppose that your hypothesis class consists of all possible C programs. Okay, so all programs of finite size that are written in some particular language like C. Okay, and let's say that you compress this using a tool like gzip or zip. As it turns out, many of the natural compressors, they're all prefix free. All right. So if you take a compressor like gzip, they fundamentally have this property of being prefix free. So the inherent reason for choosing prefix free codes and the background behind Crafts inequality is basically compression. So suppose you had a description for each of these predictors in some language. Now, C is something abstract, something concrete, but some way of describing it in a prefix-free language. Then the weight function essentially tells you how long is the description. Okay, the longer the description, the more complex the predictor is. If you take the example of H being, let's say, a predictor written in the C, in let's say C, right? The longer your code is, the more complex your code is. It's a natural choice. Right? It's an intuitive way of describing the complexity of something. In this case, the length of the zipped file, right? You take the C program, that is your predictor, and then you compress it using a tool like zip, and you look at the length of the compressed file, the size of the compressed file. That gives you the length of f of xk. Right? Because xk is your C program, f of xk is the compressed file. And the size of f of xk, so let's suppose that each say h is the set of vectors that can as let's say C code. Right? So each predictor is let's say a sequence of instructions in C which can be expressed as some kind of a text file. F of h is the gzipped version of the C file that you have. All right, and gzip has the prefix free property. So the length of f of x is the size of the gzipped file. So the weight function that you choose is basically 2 to the minus size of the gzipped file. So if
So like does gzip plus prefix key mean that the ASCII characters are converted to some
so gzip it results in some binary file, right? If you view this as a binary string, then the corresponding
this
by-
would be the prefix of no other compressed C program or like
Yeah. No, the text file in fact.
how does it like
So it's based on an algorithm called Lempel-Ziv. It seems a bit counterintuitive, right? Because you're getting compression, but at the same time you're saying that no zip file is a prefix of any other zip file, right? It.
why is that like even necessary?
What do you mean? Okay, so many of these came under the consideration. Let's suppose that you want to transmit compressed files, right? Now, how do you know where the first compressed file ends and the second compressed file starts? Transmission is over binary, right?
Have like one prefix to character to demarcate, I mean set of string to demarcate the
Which means that that particular string is not available to you as part of your compressed file.
yes.
Right. That's one natural way, but that's inefficient. And as it turns out, of course, under certain assumptions, adding this prefix free property, you don't lose too much. In the sense,
Prefix free, how do you determine the end? Okay, you found your
because it's a prefix free code, right? So suppose that you can write all the symbols in the tree, then you just traverse down the tree until you hit your file. That's it. So it's a natural decoding algorithm. Right? Yeah, I mean, that was the primary motivation when you had to send compressed symbols. When you want to transmit compressed symbols, you want to know where the first symbol ends and the second symbol starts, because these are all variable length strings, right? So the only way of determining it is if there's some natural algorithm which tells you where it stops. Now that's okay if that's what the prefix free property guarantees. But as I said, you can extend this to this idea of unique decodability, wherein maybe you don't get to know immediately that the first symbol has ended. But when you read the next few bits, you get to know, the previous symbol ended 2 bits prior to this. Right, so there are these, yeah. So the size of f of x is basically the size of your gzipped file. Now if we plug this back in to our bound on the generalization error, what would this give us?
Does gzip also guarantee compression, or it's like most likely compressed?
It guarantees compression. So gzip, like a lot of the other zip algorithms, the underlying algorithm, the compression algorithm underlying it is what is called Lempel-Zip. The Lempel-Zip class of algorithm. There's a few more things. For example, you want to ensure that it has a certain format. So there are certain things that are prefixed and suffixed and so on, just to ensure that it has a certain format. That's zip. All of these variants of zip. But the underlying prefix-free algorithm is the Lempel-Zip algorithm. And what the Lempel-Zip algorithm guarantees is that the length of the compressed sequence is going to be something that depends on the entropy of the input string. All right.
But like it guarantees compression.
Again, it guarantees compression in the sense that certain strings, of course, it's impossible to compress every string in the universe, right? That's not possible. You can't have a one-to-one map where every sequence is, and plus if you also have the prefix-free property, you can't guarantee that every sequence is going to be mapped to a sequence which has a smaller length and still be able to recover that uniquely. All right. So obviously certain sequences will have to have a larger size than the original sequence. But these are the so-called bad sequences.
Like strings with lesser entropy are compressed.
Are compressed very well, yes. So what this says is that if I use if we choose
How do you measure the entropy of the string?
diversion, so just give me 2 minutes. Wk to be 2 to the power minus the size of f of xk or f of hk. Then you basically get so this is the bound on the generalization error that you get. So the longer, the more complex the description of your predictor is, the higher the generalization error is going to be. All right. So in some sense, so even if you look at the SRM rule is basically going to be HS is going to be arg min overall H of RS of H plus constant square root f of length of f of H plus log 2 over delta by n. So your regularization term gives you a higher penalty for those which have a more complex description, right? Which is the basis behind the so-called minimum description length principle. If you have two predictors which give you the same empirical risk, then you prefer the one which has a more simpler description. And in this case, the description is provided by this prefix-free code. So you can think of the prefix-free code as some general way of representing the or describing the predictor in some language. In this case, it's binary. All right. There's a much more deeper and rich theory behind all of this, but this is just a way this is used in machine learning. Questions?
This also works for ERM, whatever normal agnostic background.
You could, but you don't need the generalization error term. Of course, so one thing you have to keep in mind, because all of this essentially assumes that
So you
it's a countable class. It's a countably infinite class. Right? Because right now I'm labeling you need a prefix-free code for your hypothesis class, which works only if the class is countably infinite. So this is at the level of each individual predictor, but if your hypothesis class is a countable union of pack agnostic classes, then you have a description for each HK. So you just replace this quantity by a description f of HK. Right? You have a complexity measure for that particular hypothesis class or hypothesis subclass, and you choose between two predictors from two different subclasses. You choose the one that has a simpler description. That's what the minimum description length principle says.
How can we come up with finite, countably infinite predictors?
So that's why, if in general you will not be applying this prefix-free code for each predictor, but rather to each subclass.
But what I wanted to ask is, so when the VC dimension is infinite,
Correct.
how can we come up with this solution? It only works when we know this. I can able to write countably infinite.
Yes, that's true.
Yeah.
You have to know that you know the hypothesis class, and the starting point is that the hypothesis class is either has VC dimension finite, or it can be written as a countable union of subclasses, each having finite VC dimension. For example, the class of polynomial classifiers.
But how they come?
So, because you can look at the subclass of polynomials of degree at most k. The kth subclass is the subclass of all possible polynomial predictors of degree at most k. Each of those has finite VC dimension. But if you take the union of all of them, then it has infinite VC dimension. Right. The minimum description length principle is far more general in a sense. We've only seen it applied to this. But it's a general principle that people like to follow. Always choose the simpler description, always choose the simpler solution compared to the more complex one.
So the set of all polynomials is already uncountably infinite.
It is uncountably infinite,
Then we
yes.
have to countably infinite.
Subclasses. right? So then you define the code for each subclass, not for each predictor.
It doesn't mean like a lower degree polynomial is preferred.
Yes, exactly. You prefer a lower degree polynomial over a higher degree polynomial.
How does this step work in practice?
Which one?
SRM.
Again, it's not very easy to implement SRM in practice. In general, again, remember that all of this that we are doing is binary classification with 0-1 loss, right? In general, 0-1 loss is not amenable to many of the techniques that are commonly used in practice. You almost always use a different, what is called a surrogate loss function. But even then, you try to choose a regularization term that makes use of this principle, that biases you towards predictors that are simpler rather than more complex. All right. The problem with all of this in general is that in practice, you want ultimately ERM or SRM, they boil down to solving some kind of an optimization problem, right? The question is, how do you solve this optimization problem efficiently? Almost always, you want an optimization problem that is continuous and smooth. That's typically the scenario that ML practice works in. Convexity is a luxury that you generally don't have. So you generally, if you have a convex optimization problem, that's great, you're done. But it's okay. That's something that you sacrifice. You have to sacrifice. But smoothness and continuity and smoothness is something that is almost always required. As soon as this becomes a discrete optimization problem, things start to blow up. Because even if it's a discrete optimization problem, almost always you solve it using some kind of a continuous optimization framework. All right. And so you have to choose your regularization term such that it's smooth enough. So then it boils down to either using heuristics or whatever. But so in practice, you don't use the algorithms exactly in the way that we framed so far, right? But even heuristics are based on some underlying theory, right? So how much should you prefer certain things over others? How should you choose your regularization term? Well, a general rule of thumb is that you should choose your regularization term which biases you towards simpler predictors rather than more complex predictors. And how would you describe simpler predictors? Something that embodies the minimum description length principle. Even if it is not exact, at least approximately. That's going to work out reasonably well. So instead of trying something blindly, it helps to base your algorithms on these fundamental principles. Right?
Suppose in a neural network, let's say there are W weights,
Yep.
and I convert each of the weights to binary form, and then I just concatenate them. Can I consider that as a valid mapping? Like we are mapping a H function to binary number.
Yeah, it has to be prefix free. Right? One thing is, okay, you take the weights, you concatenate them in binary form, and then compress this using something like gzip. Then what you said makes perfect sense. Any other questions? I'm sorry?
Why exactly did we concatenate the weights? Are we using it as a regularizer term?
Yeah, so suppose you have a complicated neural network for which the VC dimension is infinite. Then what do? You have to use the SRM principle. And how do you choose the weight function? This is one way of choosing the weight function. Of course, in the end, it doesn't give you an optimization problem that is easy to solve. It's a different story. But in principle, that is one way of going about it. Hypothetically, that's one way of solving it. Any other questions? So now we'll make a slight switch. So far we were talking about very general hypothesis classes and what we can say about predictors based on these hypothesis classes. We were essentially trying to derive generalization error bounds for arbitrary hypothesis classes. So now we'll fix a specific subclass. We'll exclusively look at linear predictors. We'll then go back to more general stuff. But let's explore linear predictors in a little more detail. All right. So linear predictors are those for which h of x can be written as some phi of w in Rt, b in R, where phi is some nonlinear function depending on what kind of a problem you want to solve, right? So if you choose phi of x to be indicator x greater than 0, then this corresponds to a linear classifier. If you take phi to be the identity function, then this is just linear regression.
H of x greater than 0, 1.
I'm sorry?
Identity h of x greater than 0 or just x greater than 0.
Okay, maybe I should have used a different variable here to avoid confusion. See, phi of z is indicator z greater than 0 because remember this is phi of w transpose x plus b. So phi of w transpose x plus b is the same as saying indicator w transpose x plus b greater than 0. Right. There's another so right now I have basically for this particular hypothesis class I have d plus 1 free variables. Right, the d elements in W and one element in B. This is commonly called the weights and biases. And there's another sort of alternate form that is that will also be useful in the case where I can say I can put W tilde to be equal to the vector W1, W2 up to WD. I append B to this. I combine the weights and bias into one single vector. And I say x tilde is the vector x1, x2, xd, and I append a 1. All right, then you see that w tilde transpose x tilde is the same as w transpose x plus b. And indicator W transpose X plus P greater than 0 is the same as saying indicator W tilde X tilde is greater than 0. This doesn't buy us anything computationally, but on the right hand side you have sort of a homogeneous form. On the left hand side you have an inhomogeneous form. And we'll make use of that a little later on. So let's try to see all the stuff that we've seen so far in the context of linear predictors. Right? Suppose we wanted to learn the concept class H. Again, I'm talking about binary classification with 0-1 loss. Then what does this correspond to? It means that the ground truth is being generated by some H from the class of linear predictors. So this learning the concept class H also corresponds to what is generally referred to in the literature as the linearly separable case. It means that there is some predictor there is some hyperplane that splits the points labeled 0 and the points labeled 1. Right? Because ultimately, what does a linear predictor do? A linear predictor is essentially just a hyperplane, and which separates all points on one side of the hyperplane are labeled 0, and on the other side of the hyperplane are labeled 1. All right. So for this, what does the ERM correspond to? So can you give a description of the empirical risk minimizer? So suppose I give you a data set that is linearly separable, which means that basically it's being generated from the concept class. So there is actually so given the data set, there is at least one hyperplane that splits the points labeled 0 from the points labeled 1. All right. So in this context, what is an ERM? Can you give a verbal description of? I'm sorry?
Average of this classification.
I'm asking for the empirical risk minimizer.
Like you need an algorithm or
Not an algorithm.
hyperplane that's separate?
Exactly. So any hyperplane that separates the points labeled 0 and the points labeled 1 is an empirical risk minimizer. Again, there could be multiple such hyperplanes. It's not unique. Okay, maybe just a little change. So I'll use labels -1 and +1. Okay. Well, this is okay. It's a nice description, but ultimately we need an algorithm. Right? How do we find an empirical risk minimizer? How easy is it to find an ERM? In general, computing the ERM is hard. right? But for linear predictors, in the linearly separable case, there's a very efficient algorithm to do this, right? So the efficient way, one such efficient way is to pose this optimization problem in a nice form, right? So what does this correspond to? We want to find W and B such that W transpose Xi is greater than B for all Xi such that Yi is 1, and W transpose Xi is less than B for all Xi such that Yi is minus 1. Alright, so in this context, my phi, I'm assuming that,
Closed form solution.
sorry, just give me a second. So my non-linear function here is the sine of z. Yes, question?
Is there no closed form solution?
There is no closed form solution possible.
Is it possible to prove that there is no closed form solution, given that it's linearly separable?
I'm sorry?
If it's linearly separable,
Correct.
there's no closed form.
There is no closed form possible.
Can you prove that there is no closed form solution?
I don't. It's in general. How would you get the closed form solution? You can't.
But like if it's just 2 points, then you can give a solution.
For 2 points, yes. But in general, you're given an arbitrary number of points, right? And sometimes you don't want a closed form solution. As we'll see a little later, closed form solutions may not be what you want. There are perhaps better ways of doing things. Okay. All right. So effectively, you can write this as, you can pose this as an optimization problem with a bunch of linear constraints. So you minimize a constant subject to the constraint that W transpose Xi is greater than B for all Xi such that Yi equal to 1, and W transpose Xi is less than B for all Xi such that Yi is minus 1. So these are a bunch of linear constraints and you are minimizing a trivial objective function. So this is a linear program. And this is effectively what is called a satisfiability problem, because the objective function is trivial. You just want one solution that satisfies these constraints. But this particular formulation is almost never used. There's an annoying feature about this particular formulation, which is that if you have, let's say, some W comma B satisfying this, then alpha W and alpha B also satisfies this. which kind of blows up your space of solutions. So it's convenient to maybe reparameterize this such that things are nicer in a sense. So let's take, and one way of reparameterizing is sort of you fix one of the parameters, let's say b. You fix b to be something, and then the free parameters are only going to be in w. Right? It's a very useful way of reparameterizing. But how do you choose this particular b? Well, one way of saying is let's define gamma to be, now given the data set, let me define, okay, but maybe even before that, there's another way of stating this.
So the annoying part is that it can be scaled.
That's one of the annoying parts.
Strict inequalities.
The strict inequality is also another annoying part, but yeah, the strict inequality is a problem because it's not a closed set. Ideally, when you want to frame an optimization problem, a nice optimization problem is one where all the functions involved are convex and all the sets involved are closed. So strict inequalities are always a problem. You always want to replace them with non-strict inequalities. All right. I claim that this is the same as minimize 1 subject to yi times w transpose xi plus b greater than here I wanted minus b. Right, because if yi is plus 1, then you want w transpose xi plus b to be greater than 0. If yi is minus 1, then you want w transpose xi plus b to be strictly less than 0. All right. So let's define gamma I to be the smallest possible value the left-hand side can take. Minimum over I, yi times w transpose xi plus b. I'm sorry, not just w transpose xi. Okay, where w is one hyperplane that separates the two. We know that there exists at least one hyperplane that separates the two. Yeah, just 1 second.
I wrote that as B instead of minus B.
Yeah, I originally wrote that as b, but then I corrected that to minus b later. Right. So let me have this plus b over here, where this w comma b corresponds to the separating hyperplane. So to one such separating hyperplane, we know that there exists at least one. All right. So or min over I yi times w tilde x tilde I. Um, so now if I take a new W, which is W tilde by gamma. Right? This is then if I look at W, whatever, double tilde xi within the data set, this is guaranteed to be at least 1. Right? Because it's after all equal to yi times W transpose xi divided by min overall I of W transpose xi. So that's greater than or equal to 1. So this means that there is some hyperplane W. There exists some such that yi times W transpose xi is greater than or equal to 1 for all I. So given any data set that is linearly separable, it is possible to find some vector W such that yi times W transpose xi is greater than or equal to 1 for all I. Now I've got rid of the second annoying feature, which is that I've got rid of two annoying features. One, I don't have a strict inequality anymore. The second, if W is a solution, then alpha times W is no longer a solution. It's not necessarily a solution.
It is for alpha greater than 1.
It is for alpha greater than 1, correct. So we'll impose another constraint later. Such that so this is one solution for our, and this is something that can be very easily implemented using any LP solver. I don't have a closed form expression, but I have a way of numerically solving this, and it's fairly efficient. Questions?
Why are you actually multiplying this y with W transpose xi? Because W transpose xi is definitely some y, right?
It's your y hat, right? Basically what I want is y hat to have the same sign as y. Right? That's why I'm multiplying the two together.
Wait, it's not?
Exactly. Yeah.
Like the sign of that is y.
Which one?
Sign of W transpose x.
Correct, you're right. So basically I want W transpose xi to have the same sign as yi. So my y hat is in fact the sign of W transpose xi. It's correct only if the two have the same sign. Okay, so let's stop here. We'll continue in the next class.
How does this stop this annoying feature of alpha, omega, and
It doesn't fully solve that. Certainly, I can't choose a negative alpha anymore. All right, but I can choose a positive alpha and it will still work.